Ladies and gentlemen, we will now move to the next chapter, looking at the quantum mechanical description specifically of atoms, and also linking that up with the spectra of atoms. So we're going to look at the internal structure of atoms using the quantum mechanical principles we've learned. So in the first two chapters, we have defined some definitions and also some tools that we're going to use now on atoms. And remember, we are now starting to look at things that chemists use. For example, atoms are things that we use on an everyday basis. We use it to build molecules, etc. And specifically, we're going to look at the electronic structure of an atom. So if you have an atom, you have a nucleus. How are the electrons arranged around this nucleus? And a lot of the concepts that we're going to look at are things that you've heard of before. So we're just going to recap it quickly, but you're now going to see where these ideas come from quantum mechanics. Now, the first definition that we're going to look at is something called a hydrogenic atom. And that is any atom with one electron. And it has a general atomic number, Z. So the only neutral hydrogenic atom is one single hydrogen atom. If you take a helium atom and you remove one electron to give it a positive 1 charge, you also have a hydrogenic atom. And in the same way, you can form hydrogenic atoms using any atom by removing enough electrons so you only have one electron left. So even for uranium with 92 electrons, if you remove 91 of those, which might not be experimentally possible, but theoretically we can do that, you have a cation with a charge of plus 91, you have a hydrogenic atom, a one electron atom. Now, what makes a one electron atom very special is that you can solve the Schrödinger equation for this atom exactly. So for a one electron atom, you can solve the Schrödinger equation exactly. If there's more than one electron, you cannot solve the Schrödinger equation exactly. We have to start making approximations, as we'll see later. But we'll use the solutions to the one electron atom Schrödinger equation for many electron atoms. So many electron atom is any atom with more than one electron. It's also called a polyelectronic atom. And these are all the other neutral atoms other than hydrogen. So helium, etc. are polyelectron or many electron atoms. So we cannot solve these Schrödinger equations exactly, which is a big limitation in quantum mechanics and also in computational chemistry. Where we basically use computers to calculate chemical properties. But because we cannot solve the Schrödinger equation exactly for any other atom except the hydrogen atom, we cannot always calculate the properties very accurately. Okay, so let's have a look at these one electron atoms or hydrogenic atoms. So let's look at any hydrogenic atom. It has an atomic number Z, which is the number of protons. It has a nuclear charge Z times E, where E is the charge of the proton. And it also has a potential energy, the Coulomb potential energy, which is the positive, negative potential energy between the nucleus and the electrons, which is given by this equation. R is the distance of the electron from the nucleus. Epsilon 0 is the vacuum permittivity. And if you want to write the Hamiltonian for the electron and the nucleus, so there we have the nucleus, there we have the electron. It's a one electron system. Here's our atom. That's the distance between the nucleus and the electron. The Hamiltonian includes the kinetic energy of the electron, the kinetic energy of the nucleus, as well as the potential energy between the two, which is a positive, negative potential energy. Now remember, if this is your atom, you have the motion of the electrons, or the one electron in this case, moving around the nucleus, but your atom itself may also be moving or translating, which will be described by the particle in a box system. So you have this motion, and the atom itself might be moving as well. But it makes sense to rather split these two movements. So we split the motion of the atom as a whole through space and the motion of the electron relative to the nucleus. So we only at this stage, we've looked at translation already, we're only going to consider a stationary atom and look at the movement of the electron around the nucleus. So in this case, the Schrödinger equation for the internal motion of the electron relative to the nucleus in a stationary atom is given by this equation. Now, let's first have a look at how this equation compares to our typical Schrödinger equation. So this was for a typical one-dimensional case. You still have the minus h bar squared term, and instead of mass, you now have the symbol mu, and that is a symbol for reduced mass. Reduced mass is used when you have two bodies. In this case, we have the nucleus and the electron. What is the effective mass? Sort of an average or a weighted mass of the two. And this is how you calculate reduced mass. Me is the mass of the electron, Mn is the mass of the nucleus. Or you can calculate it in the following way, where M1 would be the mass of nucleus, M2 would be the mass of the electron. Okay, then we have that upside down triangle, and that is called del squared, and that is just partial derivatives in 3 dimensions. Just because we're working in a 3-dimensional system. Remember, an atom exists in the 3-dimensional world. So that is very similar to what we've seen before. Then we have the potential energy term, and that is just the potential energy term that I've just given you. That is the plus minus attraction between the nucleus and the electron in our one-electron system. So the Schrödinger equation is very similar to what we've seen before, except that we've changed it to 3 dimensions. We're using the reduced mass, and the potential energy is the potential energy for a Coulombic interaction between the electron and the nucleus. In this example, the reduced mass or the effective mass is similar to the electron mass, because the mass of the nucleus is much larger than the mass of the electron. You can go and check this. So only in this specific example we can actually replace the mu with the mass of an electron. So this is only in this case. But it is better practice to actually just calculate the reduced mass. Now, we make the statement here that the potential energy, which is the Coulombic interaction, plus minus interaction, does not depend on angle, but on radius. Why do we say that? And it's very important that you understand this. If you think about a positive charge and a negative charge, no matter where at a specific radius you place the negative charge, the attraction between the positive and the negative charge will be the same at any angle. So if we were to define that angle there, or there, or there, or there, the attraction will be the same. So the potential energy will be the same. But if I change the radius, the potential energy will change. So if I make the radius longer, the potential energy will change. So the potential energy of this type of plus-minus Coulombic interaction does not depend on angle, but on radius. So there's an angular component and a radial component, and we actually separate the equation into these two components. The radius component, where the potential energy changes with radius, we call the radial component. And the angular component, where the potential energy stays the same with angle, we call the angular component. So the wave function looks like this. Let's say we call the radial component uppercase R, and it's a function of R. Why? Because the radius changes like this. And then we have the angular component, and we're going to call that the following. Why do we have two angles? Remember, we're working in a three-dimensional system. An atom is three-dimensional. And we saw for three-dimensional rotation, in order to define the angles, you need a theta and a phi angle. And this symbol should look familiar. What did we use Y for? We used Y for the spherical harmonics for three-dimensional rotation. And this is exactly what we have here. So if we look at the wave function for a hydrogenic atom, it's a function of radius, angle theta, and angle phi. Remember, for three-dimensional rotation, we just had the angles theta and phi because we kept the radius fixed. Now, for the atom, we can also allow the radius to vary, the distance of the electron from the nucleus. But this we can separate as into a radial component and an angular component. Now the solutions for this angular component is exactly the same as the solutions for 3D rotation, which is the spherical harmonics, quantum numbers L and ML. So this section we've actually covered already. In your data sheet, you will find a table that lists these spherical harmonics. It's labeled table 9.3 in your data sheet, and all the functions are given there depending on the specific quantum numbers L and ML. So that section we have covered already. So what is new that we need to add is this radial part to the wave function. And that we call the radial wave equation. And that focuses on the motion of a particle of mass mu in a 1D region where the radius is changing. So that is moving closer and further away from the nucleus. We've covered the angular part at constant radius. Now we are looking at this motion. Again, we have a Schrödinger equation that looks a bit different from what we're used to. But let's just write the regular Schrödinger equation. basically we make the following substitution. Mass is again replaced by reduced mass. The wave function we now replace with u, and x we replace with r because it's a function of radius. We don't work with x, but it's the same thing basically. And in this case, the effective potential is given by this equation. There's our Coulomb interaction term, but we have to add another term. So this first one refers to the Coulomb potential, and the second one refers to centrifugal force, which is very important, because if you just add that, the electron would just collapse onto the nucleus, and we know that doesn't happen. This ensures that the electron stays in an orbit surrounding the nucleus. So our classical physics equivalent is the centrifugal force of the electron moving around the nucleus. Given by this, we see the quantum number L. And L has to do with what? Angular momentum, something moving in an orbit. So that makes sense. Ladies and gentlemen, this section you can leave. That page you can leave. And this you can also leave. If we look at the allowed energies, and I want you to please add for the radial parts, the energy equation looks like this. And you'll notice that we have an n in this equation, and n is a quantum number, which we call the principal quantum number. We also will notice that the angular quantum numbers, ml and L, do not appear in this energy equation, only the principal quantum number. So if you look at the form of the radial wave functions, it typically consists of a polynomial in R and a decaying exponential in R. And we can write these in terms of a function rho, and I want you to have a look in your data sheet. The radial wave functions for hydrogenic atoms are listed in table 10.1 in your data sheet. And you will notice the symbol rho, and then here at the bottom it tells you what rho is and what A is. So you don't have to memorize any of these equations, they are given in the data sheet for a specific value of n and for a specific value of L. The next section you can leave. Just again, there's reference to table 10.1 that lists the radial wave functions, and there's also a figure that shows you what these radial wave functions look like as a function of radius. So we can now have a look at an illustration using these wave functions. So calculate the probability density at the nucleus for an electron with n equal to 1, L equal to 0, and ml equal to 0. So we need the wave function, and we know at the nucleus the radius is equal to 0. So what we want is the wave function for an electron with n equal to 1, L equal to 0, and ML equal to 0. But we know the wave function for an electron defined by those quantum numbers as a function of those variables is equal to the radial part times the angular part. And remember, the angular part has quantum numbers L and ML, and the radial part quantum numbers N and L. So if I want this wave function, how do I go about? Well, the radial part I can get in table 10.1, and the angular part I can get in table 9.3, and then it's just a matter of multiplying the two to get the wave function, and probability density is the square of that wave function. So let's look at the radial part. So from table 10.1 for n equal to 1 and L equal to 0, in this case rho is equal to 2zr over n by 0, but if r is equal to 0, because remember we are working at r equal to 0, that just becomes 0. So this is 2 which becomes 1. So that is our radial part. Then secondly, for the angular part, from table 9.3, with with L equal to 0, ML equal to 0, we find the following wave function, or angular wave function, or spherical harmonics. Zero, 0. So the wave function of that electron is 2 but it asks us for the probability density, which is the square of the wave function. In this case we don't have to worry about the complex conjugate because there is no I, so it is equal to 4 Okay, so there we have the probability density for that specific electron. If it asks you specifically for the hydrogen atom, remember this is for any hydrogenic atom, not only for hydrogen, but for hydrogen you can make the replacement A equal to A0, where A0 is the Bohr radius, and also Z equal to 1 for hydrogen. Then you can actually get a value for the probability density. So then you can start substituting those two values, and you can find a value for probability density. Okay, so this brings us to something that you have heard about since school days, but it has never been defined properly from first principles, so now we can do that. And that is what an atomic orbital is. An atomic orbital is a one electron wave function for an electron in an atom. So it's a wave function that describes an electron in an atom, only a single electron. So we're dealing with a hydrogenic atom, so it's a one electron atom. The orbital describes that electron. It's the wave function that describes that electron. So an orbital is a wave function. And for a hydrogenic atomic orbital, we need these three quantum numbers, NL and ML, principal quantum number, orbital angular momentum quantum number, and ML, which is also related to orbital angular momentum. So when an electron is described by this wave function, we say that it occupies that orbital. And we can define the specific electron or the orbital. So the electron is effectively the orbital, is the electron or the state, by listing these quantum numbers, and we always do it in the order of NL, ML. So if I give you the numbers 1, 0, 0, you know that the first one is N, the second one is L, and the third one is ML. So N is the principal quantum number. It runs from 1 to infinity, and it determines the energy of an electron. Remember, L and ML has to do with angular solutions, angular momentum, and L goes from 0 to n minus 1, so L is limited by n, and ML goes from L to minus L. So n controls the value of L controls the value of ML. Now, if we really want to describe the hydrogenic atom state, we also need to include spin. For spin, we have the spin quantum number S, and which is always equal to a half, and ms, which may be plus a half or minus a half. So to fully describe the state of an electron, we need N, L, ML, and ms. So let's start by looking at the energy levels of a hydrogenic atom. So we're still talking about a one electron atom. So the general energy equation for this type of atom is this equation. So this is true for any hydrogenic atom. If we now replace some of the variables for hydrogen, for example, Z we can replace for hydrogen specifically, mu we can replace for hydrogen, the expression looks like this. Where RH is the Rydberg constant. So this is only for hydrogen, that's for any hydrogenic atom. Don't confuse the two. So for hydrogen, E1 is that, E2, etc. If you look at this expression here, you will see that energy is directly proportional to the square of Z. So because of that, the levels are 4 times as wide apart in helium than in hydrogen, because the Z of helium is more than the Z of hydrogen, because the energies in separation is proportional to Z squared. Now I want us to have a look at this figure. This figure is specifically for hydrogen. So the hydrogen atom. It's not for any hydrogenic atom, it's just for hydrogen. And it lists, or it shows the energy levels. Now firstly, what I want you to see is that everything is listed relative to a value of 0. and everything is negative. The E1 is negative, minus HCRH. E2 is negative. E3 is negative. So there we have E1, E2, E3. So all of these values are negative. You also notice that the spacing decreases the closer you go to 0. So the spacing between 1 and 2 is very big, between 2 and 3 is smaller, between 3 and 4 is smaller, etc. Now, this 0 level is obtained by removing this electron infinitely far from the nucleus. And that is equal to the ionization energy. So basically when you ionize something, so this distance here is ionization energy. So M gives M plus an electron. So all energies given by the equation are negative. Energy lower than that of the infinitely separated stationary electron and nucleus, so infinitely separated, completely removed, which have energy equal to 0. And that gives ionization energy. So if we look specifically at hydrogen, ionization energy in general is the minimum energy required to remove an electron from the ground state, the lowest energy state of an atom. So for hydrogen, this is the lowest energy state, that's the infinitely removed state. So the ionization energy is the difference between those two. So the ground state has N equal to 1, and we've said that is the energy, you can check that. The ionized state has N equal to infinity, and has energy equal to 0. So if you determine the ionization energy, is E infinity minus E1 is 0 minus HCRH is HCRH. And you can determine this value because we have the value for all of these constants. So you can determine the ionization energy for hydrogen. All orbitals that have the same value of N are called shells of an atom. And in a hydrogenic atom, and this is very important, all the orbitals in a shell have the same energy. We can refer to shells using either numbers or letters, and we refer to different orbitals or subshells by using these letters. So if L is equal to 0, so subshells have different values of L. We talk about an S orbital, L is 1, P, L is 2, D. You know this from first year. So N determines the shells, L determines the subshells or orbitals. So very importantly, for a hydrogenic atom, they all have the same energy as long as N is the same. So if you were to plot the energies, there's the 1s orbital, 2s, 2p have the same energies, 3s, 3p, 3d all have the same energies. You can also look at the number of orbitals. So this you know, each energy level is n squared fold degenerate. So that tells you the number of orbitals in that level. So if you look at that, for n equal to 1, 2, 3, n squared is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, because we've got 5d orbitals, 3p orbitals, and 1s orbital. So n square fold degenerate. There we have 4, and there we have 1. And you know how to get atomic orbitals using the tables to construct atomic orbitals. So we use table 10.1 for the radial part and table 9.3 for the angular part. So let's say we are interested in the orbital occupied in the ground state, so n equal to 1, L0 and ML0 for the atom. So if you use table 10.1 and table 9.3, you should be able to get this wave function. And this is the ground state. Now in this case, we don't see any theta or phi's in this wave function. So it's independent of angle. No phi or theta. That means it has the same value at all points of constant radius. So this 1s orbital, as we know, is spherically symmetrical. You know that an s orbital is a sphere. You knew this in school days. But now you can see why. Because if you look at the wave function, it doesn't have an angle in that wave function. And we have this exponential decay from the radius. And if you just look at this wave function, which is not the full story yet, it seems like the most probable point to find the electron is at the nucleus itself, which we know doesn't make sense. But we will clarify this soon. Now there are different ways in which we indicate orbitals. We can use the probability density using shading. So there's a darker probability and a lighter probability for the 1s orbital. For the 2s orbital, we go through areas of high probability, zero probability, increased probability, and high probability again. Or one can just use a boundary surface that indicates the 90% probability level in the 1s orbital. So these are representations that you are familiar with already. If one looks at the sizes or variation of the radius of these orbitals, we find that that is the trend that is typically observed. So a d orbital on average, and I talk about the mean radius, is smaller than a p orbital, which is smaller than an s orbital, for a specific value of n. Okay, and we can look at the properties of an s orbital. So they're all spherical, they have different number of radial nodes. So in each s orbital has n minus 1 nodes depending on n.